All right, so today we're going to start talking about balancing chemical equations. That's really what we've been driving towards since last unit. Unit 6 kind of gets you ready to start doing that, where you're balancing out chemical formulas, you're starting to learn some chemical naming, and that's all going to apply here to balancing equations. Now, balancing equations is what you probably think of as chemistry, so we're going to hop right in. First thing we want to talk about is this idea that products usually follow a word like produces, yields, or forms. So anytime you see words like produces, yields, or forms, we're talking about a product. You're talking about something that you're making. So for example, in the Haber process, you don't need to know what that is. That's just the name of the reaction. Hydrogen gas and nitrogen gas are going to react together to form ammonia. So it's making ammonia, NH3. All right. So what we tend to do is when we write a reaction, you're going to use an arrow to say that a reaction takes place. And so your product, the NH3, goes to the right of the arrow, right? We make NH3, we make ammonia. So with that being said, we need to know the two big vocab words for this unit. The first one is reactants. So reactants are going to go on the left-hand side of the arrow. Those are the things that you are reacting together. So for example, if we had element A and element B, we're reacting them together, right, in this reaction. That arrow tells us that a reaction takes place and we're going to form some kind of product, right? Or products. Some situations you might form more than one thing. So in this case, the product we form is AB, right? So we take A and B, we put them together to make our product AB. So reactants, what you're reacting, products, what you're making. All right. One thing to keep in mind, keep an eye out for the diatomics: chlorine, hydrogen, oxygen, fluorine, nitrogen, bromine, and iodine, right? They aren't by themselves in nature, so anytime you have oxygen or you have hydrogen or you have chlorine, it's not just one Cl, it's not just one H, it's not just one O, there's two of them. And a lot of times they're going to be found as gases. Now I'm going to talk about that in a couple minutes, but for right now, let's ignore that. Let's look at an example. So this is going to be the type of problem you're going to have to solve as we kind of make our way through this. You're not going to start with word problems right away, but we will work our way up to them. So for example, you have something like potassium chlorate. Now, remember back to last unit where potassium is K plus 1, chlorate, ClO3 at a -1 charge, right? And it tells us it's strongly heated and decomposes to yield. So there's our arrow. Oxygen gas, remember oxygen's never alone, so it's O2. And potassium chloride, so remember potassium's +1, chlorine's a -1. So that gives us the formula KCl, right? So in this case, right, we have KClO3, potassium chlorate, breaking down to form oxygen gas and potassium chloride, KCl. What you're going to want to do from here is figure out how many it's going to take to get there. For the easiest way to do it, in my opinion, is using bingo chips or poker chips to do this. You can make each element a certain color, but if you don't have that at your disposal, you can always just draw these out using letters. So to say KClO3, we're going to do KCl, 3 O's, right? So we're going to start making things on the right-hand side of this arrow. So we need to use what's on the left-hand side to make things on the right-hand side. So, for example, let's make a KCl because we have the K and a Cl. So they're used to make that KCl, right? We can also make an O2, right? We have 2 O's, so let's make O2. Here's our issue, though. Notice we have an oxygen left over. We can't just get rid of it, right? You can't just throw it away. The law of the conservation of matter says you can't create it or destroy it, so you can't just get rid of it, you can't just make it appear. However, we could always add in more KClO3. In this case, right, we can make another KCl. So now we have 2 KCl's. I'm just going to draw this line so you can see these are drawings. I have 2 more O's, right? And here's the thing, another leftover. But notice I have 2 leftovers now that can go on to form a third O2. So what it ended up doing was it took 2 KClO3s to make this reaction completely go, to make sure that we used up all of our reactants. We made 3 of these O2s, 3 of these oxygen groups, right? 1, 2, and 3. And we made 1, 2 potassium chlorides, 2 KCl's. And that's ultimately what you're doing. You're coming up with a way to make sure you use all of your reactants to make your products. All right? And you're just going to put numbers down to say how much you use and how much it makes. All right? So, one thing we are going to start working with is this idea of phases. We're going to have to put them next to things. So, for example, you might work with potassium metal, right? Metals are solids. So, you're going to put a solid next to it, a little S in parentheses. You might be working with water. Water, for the most part, comes as a liquid, right? You might be working with oxygen gas, right? So you might see something written like O2 with a G next to it that's telling you that oxygen exists as a gas. The one that you haven't seen much before is aqueous. Aqueous just means that it's dissolved in water. A lot of times we talk about acids this way or different things that are dissolving in water. So, for example, hydrochloric acid, right, is never really pure. So we call it aqueous, that it is a little bit watered down. All right, one other thing you want to keep in mind is that air is a mixture of two gases, oxygen and nitrogen. So when something burns in air, right, what we're really talking about in that case is oxygen. Even though there are two things that mostly make up our air, when we try to talk about that, we're going to talk about burning in air as O2, right? So something's reacting with O2 because you need oxygen for a fire to happen. So when something burns in air, O2 is a reactant, right? You can't have fire underwater, mostly because there's no oxygen there for it to light on fire. Same thing in space. You can't really have a fire in space because there's not enough oxygen to actually make that burn. One way to see this happen is that if you put a lid on a candle, right, the candle goes out. It runs out of oxygen to burn. So oxygen is going to have to be a reactant when you see something burning or if it burns in air. Watch out for ionic and molecular compounds. Just keep in mind that you're naming things the correct way or that you're taking the names and making the right formula. We just got out of this unit, so it's hopefully nothing too crazy for you. But just make sure you remember your naming styles because that will come up again. Watch out for statements that are going to give products first. So, for example, I could tell you that something is produced from this reaction. When I tell you it is produced from that reaction, there's your product, right? So whatever I told you was produced, right? So I could say ammonia is produced from nitrogen and hydrogen, right? So your product in that case is the ammonia. Your reactants are the nitrogen and hydrogen. And last but not least, be careful with polyatomics. A couple things you want to keep in mind is to see if it's staying intact or if it's not, if it's breaking apart. So in this first example, right, notice that the CO3, that carbonate ion, breaks up into oxygen and carbon dioxide, right? So just be careful. Sometimes you're going to have to see that polyatomic break up and kind of go from there. In other cases, it's going to stay together. So notice that down in the second problem, ammonium's both in the beginning and the end. You have carbonate in the beginning and the end. So work to that advantage. Think of your polyatomics as one thing, right? Think of them as moving around as well. Sometimes they break apart, sometimes they don't. Don't make it harder on yourself. All right?